Thank you. Yes, I'm here. Glenn, are you able to load your slides?
Should I share screen? Is that what I should do? Share
I
screen?
think I think so.
Okay, let me do that. So can you see my screen now? Anyone or everyone? Can
We
you see
did,
my?
yeah, we can see it now. So
Good. Okay.
Good. Good. Thank you very much, and it's my great pleasure and honor to have this opportunity to present to you the next speaker, Professor Glenn Webb from Vanderbilt University. Glenn is a pioneer in many fields of mathematics, in particular in population dynamics and in cancer growth models. Glenn is a mentor and a dear collaborator and colleague, and for many of us here in the audience today. And I have known Glenn for over 30 years. The first mathematical biologist I contacted in Tennessee once I arrived in Memphis in 1987 was Glenn, because I was really reading his book on the theory of nonlinear age-dependent population dynamics, published in Master Decker in 1985. I know Glenn has lots of significant work, but the one which I like the most is still this early monograph. And every time I was excited, I think I have invented a new age-dependent population dynamics model, or I thought I invented some new theory. Very often I found very frustrated that it was already included in that 85 page monograph. And I noticed that as well in many of the recent publications as well. With that, then I would like to give the time for Glenn, and thank you, Glenn, for coming.
Well, thank you. Thank you very much, Jian Hong, for your very kind introduction. And it's true, we have been good friends for a very long time. Can everyone hear me okay? Am I coming through?
Very well.
Okay. And I want to say good morning to everyone. In my place, it is still morning. And I hope everyone is well and will stay well in this troubled times. We've just heard a very informative talk from Jacques, and I want to try to add to his reports, his information. So I will be discussing a certain model of COVID-19. Can you hear me okay? Okay, but if there's any questions, and if you can't hear me at any time, let me know. The models that we develop are intended to help with not only understanding the evolution of a COVID-19 epidemic, but being able to predict sometimes, at least in some future, what might happen in a particular example. And the features of the model that we will emphasize are, first of all, the incorporation of asymptomatic infectiousness, which is very, very important, we know, in COVID-19. And also, of course, symptomatic infectiousness is also important. But we will focus in a key way on asymptomatic infectiousness. And we want to use data that's available, the reported case data, to parameterize and initialize our models. And this is a tremendous challenge because the parameters of an epidemic model are vital in using the model and applying the model. And it's extremely difficult typically to identify these parameters. So this is a real challenge. Then we will also try to interpret various social measures that are used to try to reduce the epidemic in various locations. So we will try to understand the impact of those measures. So these are our objectives. Now I should say here that we have a team. Maybe I'll make this a little bigger so we can see it better. And this is joint work with Xia Lu at Beijing Normal University, and Pierre at University of Bordeaux, and also Ousmane Sidé at École Polytechnical University in Senegal. And so what about the model? Well, it's an ordinary differential equations model, just like Jacques talked about. And it has 4 compartments. The model is very simplified in many ways, but we try to incorporate essential features of a COVID-19 epidemic in a region. So here are the compartments. We have the susceptible population at time t, and this is, we just take the population of whatever region that we're looking at. And we have, as I mentioned, the asymptomatic infectious population, and these we'll call I of t at time t. So capital I of t are those individuals who are infectious but not yet symptomatic or have very low level symptoms. Then the third class is what we call R of t, reported symptomatic infectious individuals at time t. And this is based on reported case data, as I say. And this is an extreme challenge in the model to understand the data and to incorporate it into the model. And the fourth class consists of unreported symptomatic infectious individuals at time t. So those are our 4 compartments. And the epidemic is divided into 3 stages. And the first stage, we call it stage 1, is this exponential growth stage that Jacques talked about. So it's the early stage of the epidemic, when the number of cumulative reported cases, I should say, is growing exponentially. We try to identify that stage of the epidemic and base our initial parameterization on that stage. Now there's a still earlier stage when the epidemic is underway in a region, but the cumulative cases are growing more or less linearly. They're the same number every day. And so it's growing linear, but then it enters into this stage 1, the exponential growth phase. Stage 2 is when major social measures are implemented. And this is early in the epidemic evolution, but measures are introduced to reduce the epidemic, reduce infectiousness. And so we call that the second stage, and we try to understand what's happening in that second stage. The third stage is still later, when these social measures that were introduced in stage 2 are relaxed. And then transmission can increase. There could be a second wave or additional changes that we try to incorporate in this third stage. Okay, as I mentioned, parameterization of the model is an extreme challenge. And so this is always true for epidemic models. So we have tried to approach this in a certain way in which we identify our basic parameters during the stage 1 phase. And so, you'll see what I'm saying here. We have a general formula for the transmission, and it's this function tau of t, s of t, I of t, u of t. So tau is a time-dependent function. The transmission rate is time-dependent. And this is very important because there's not a single constant that can cover the transmission process in a COVID epidemic, because it's changing with time. It's changing in many ways with time, and we have to try to incorporate that change. Now, the rate depends on time, as I said, but it, of course, depends on the susceptible population, which may decrease, of course, over time. It depends on this asymptomatic infectious transmission class and the unreported symptomatic infectious transmission class. We don't include the R of T, which is the reported symptomatic infectious class, because we assume that they are isolated once they are reported. Now, parameters that are key, one is the period of time that an asymptomatic infectious individual is infectious. And we will take that to be 1 over eta. So eta is a parameter that we must understand. It depends on the location. It depends in part on timing. And our time units will be days. And so 1 over eta will be the number of days an infectious asymptomatic infectious individual is infectious. And that could be 1 over 8, it could be 7 days, 1 week. That's a controversy, and that's a value that we have to decide upon. Also, we have the reported symptomatic individuals and the unreported symptomatic individuals who are also infectious for a period of time. And that period of time will be 1 over eta days. So if 8 is 1/7, then they will be infectious for a period of 1 week. So these values, eta and nu, are critical for our understanding of the transmission dynamics of the model. Let's see, what else here? Okay, so the fourth thing is the fraction of asymptomatic infectious individuals who become symptomatic reported. So this fraction is also very controversial. So F is the fraction that become reported and when they become symptomatic. And 1 minus F is the fraction who are unreported. And so it depends on location, it depends on timing, it depends on understanding of, which is difficult, the understanding of the unreported infectious cases. And sometimes it's claimed to be half as many, twice as many, 5 times as many. It's quite a controversy, but we have to confront that issue too. Okay, here's our model diagram. So it tells us what's going on in this model. We have our susceptible class S. Those are the individuals at time t who are capable of becoming infected. And they become infected at a transmission rate dependent on this term that I just talked about. They enter first this asymptomatic infectious class. We call that capital I. And they remain in that class for a period of 1 over nu days. And then a fraction of those go to the reported symptomatic class, and if the remainder go to the unreported symptomatic class. So nu 1 plus nu 2 equals nu. They add together to give us the total removal rate for this class I to these two classes R and U. And then individuals remain in these classes for, again, 1 over eta days, and then they are removed, they're no longer infectious. So this is the basic idea of the model, the flow diagram. Here are the equations that arise as we see naturally from this diagram. We have our initial conditions, and this is our basic model. Okay, let's understand the stages of the model and the parameterization of the model. So we assume in stage 1 that there's an exponentially increasing growth rate to the cumulative reported cases. Now, the reported cases are the data that we have. They're reported daily, and we add them together, of course, to get the cumulative reported cases, which we call capital CR. So CR of T at day T is the cumulative reported cases that have been reported so far to that date. And we assume during this stage 1 that function, capital CR of T, has an exponential form. It's equal to a constant A times e to the bt minus a constant c. Now, typically we take c to be 1 because it doesn't matter too much about that value. But the a and the b value are critical in understanding this exponential growth phase in stage 1 of the cumulative reported cases. So we find an interval of time during that exponential growth phase, during the early phase of the epidemic, when we assume that the epidemic is growing exponentially, cumulative reported cases. And then we fit with some algorithm this formula here to that data. And once we have that fit, we can identify parameters and initial conditions and the starting time of the epidemic. We have a way to do that, which is given in our papers, our previous papers. Okay, the starting time of stage 1 will be T0, and it depends on the values A, B, and C. And so once we have fitted that particular exponential growth phase across some interval, we get the A, B, and the C. We plug them in here, and that's the starting time of our epidemic. Of course, the starting time of an epidemic is in reality is the index case. One individual enters the the population and begins the epidemic with transmissions which continue and grow. But that's very difficult to identify typically or to work with. So we assume that we have a time zero when the epidemic starts based on this formula here for A, B, and C. Okay, so once we have A, B, and C identified for the stage 1, we get our transmission rate. And our transmission rate has this formula. It's a function of time, function of susceptible population, the I population, the U population, and it has this mass action form. And tau 0 is the key parameter, and it will be constant in this stage 1. And tau 0 is expressed in terms of this B value back here in this formula fitting. We get a B value, and so from that we get tau 0, this rate tau 0 in stage 1. Now we've assumed a value for nu and for eta, and of course we know S of T0, the population at time 0. The initial time, as I mentioned, is T0 given by this expression in terms of A, B, and C. And then we get the initial values at time 0 for the asymptomatic infectious class and the unreported infectious class, and also the reported infectious class, and they depend on these various values. These formulas are justified in one of our earlier papers when we use this approach for parameterization. And also we can use these values to get the R naught that Jock talked about, that we know so well, that characterizes what an epidemic is doing. And R naught has this formula here, which we obtain from the next generation method, which is one way to develop the value of an R naught for a particular epidemic. So these formulas arise from this fitting of the data in the exponential growth stage, and they are critical in developing our model and applying our model. Now in stage 2, remember this is the stage in which the government imposes social measures, closings, distancing, mask, isolation, quarantine. All of these measures begin in stage 2. And so our transmission process is different in stage 2. And we have a new formula for it in stage 2. It depends on this tau 0 that we identified in stage 1. And it has this mass action form that we had in stage 1, but it's multiplied by this exponential function, which involves a parameter mu that we have to identify, and times the value t minus t1, where t1 is the beginning of stage 2. So stage 1 lasts from t0 to t1. Stage 2 lasts from t1 to t2. And the transmission rate in stage 2 has this formula where we must identify this value mu. Now we assume in stage 2 that reported individuals who are symptomatic are not generating new cases, because at least in some locations, this is certainly true, that they are isolated and they don't contribute significantly to the number of new cases. A standard ordinary differential equation model is based somehow on averages. So that's underlying this assumption. Then we have the transmission parameters in stage 3. And in stage 3, we assume that there's a relaxation of the measures that were imposed in stage 2. And so various measures that were imposed are relaxed to some extent over time. And in this way that the epidemic may begin to renew, to increase again. And we try to understand that in the stage 3 with a series of intervals of time starting at T0. Stage 3 starts at T0 when stage 2 ended and goes to T3. And then from T3 to T4 and T4 to T5 and so on. There's a succession of intervals starting at the beginning of stage 3 at T0, when the formula for the transmission is based on a multiplier alpha n corresponding to that nth subinterval times the value T0, which was identified in stage 1, times S of T times I of T, a mass action form. And the alpha N is less than 1 because we assume that in the stage 3, it won't be as bad as it was in stage 1 when tau 0 was controlling the growth of the epidemic. We also don't include the U of T in stage 3 because we assume, this is a controversial assumption, but we assume that in this, when measures are relaxed, individuals who are symptomatic and infectious are either self-isolating or they're being avoided by their family and their contacts. If they have infected family and contacts, they've done it when they were in the I class. So for simplification, we assume that the transmission in this stage 3 is not dependent on symptomatic unreported individuals. Okay, so there's another, when we try to fit data, we have to introduce what we call the capital D R of T. And this is the daily number of reported cases. So the data consists of daily reported cases everywhere. And that those daily cases can be added together to give us the cumulative reported cases. And in the model we obtain the DR, the daily reported cases from the model, from this differential equation right here. Because if you go back to our diagram, find it, you go back to the way you become reported, you come from the I class. When you were infectious and asymptomatic, then you become symptomatic and infectious, and you enter that R class at a rate nu 1 I of T. That rate nu 1 I of T brings you to the R class. So that's how you get into the R class, nu 1 I of T, daily input into the daily reported cases in the model. Now you leave that class, the DR class, each day. You stay there only one day when you report it. And so we have a 1 value here, 1 times this term. And we solve this differential equation with an initial condition. And from the model, then we have our daily reported cases from the model that we can compare to the reported cases from the data. And how do we get the CR of T? Well, again, we take the input into the R of T class, which is nu 1 times I of T, and we integrate that from the start T0 of the epidemic to the time T. And that's the cumulative reported cases in the model. And we can compare that to the cumulative reported cases in the data. Similarly, we get the cumulative unreported cases. We replace nu 1 by nu 2, and we get the cumulative unreported cases from the model. So that's how we'll use data to compare to the model. Now, we chose for this presentation, Spain as an example of what's going on in a COVID-19 epidemic. So we will apply our model, as we've talked about it, to the example of Spain. Now here's some background of Spain just to understand what's happened. The first case was reported on January 31st. By March 13th, cases had been reported in all 50 provinces, and the state of alarm had begun and social restrictions imposed by the government by March 13th. Those measures were effective in subsiding the epidemic and for several months. And then early in May 2nd, the government began to ease these restrictions in 3 phases. So there was phase 1, phase 2, phase 3 of these easing of the government restrictions. Gatherings were allowed, bars and restaurants were opened, and so forth. And these restrictions were eased beginning May 2nd. June 21st, the state of alarm was ended. I should mention that July 6th, there was a seropositive study that showed approximately 2 million people had been infected in Spain. The population of Spain, I think, is about 48 million people. So that was quite early. July 6th, 2 million people had been infected. But we have to understand that value to try to get this fraction F of reported cases versus unreported cases. July 17th, there was a resurgence of daily cases. So the epidemic started to increase. And this This can be seen in the daily data and the cumulative reported daily data. August 17th, new government restrictions were imposed to try to put the brakes on this second wave. September 4th, there was a new record of daily reported cases, approximately 10,000 on that day. By October 1st, a new emergency state was declared in Madrid with a new partial lockdown. So that's the background of the epidemic in Spain. So we want to identify the parameters in Spain. So we'll set nu equal to 1/7. So we'll assume that asymptomatic infectious individuals are infectious for 1 week. Then they transit to the symptomatic stage, either reported or unreported, and they remain there for 1 week. So we assume that eta is also 1/7. So 7 days, 1 week in each of these compartments. Now this is again a controversial assumption because maybe F is smaller and 1 minus F is bigger. And it certainly varies from location to location, and in fact, from time to time. But that's our assumption here, which is a simplification. We set the initial population of the susceptible population to 46,700,000. And then this is what the data looks like in Spain. Beginning March 1st. This is the daily number of cases, March 1st through October 5th. And this is from Worldometer. This is the website. You can go to Worldometer and see this data where we obtained it. Worldometer obtains it from the Spanish Ministry of Health. So this data shows a lot of information about what's going on in Spain with COVID-19. The outbreak was early. Our stage 1 is in here somewhere, where there's an exponential growth phase somewhere in here. Then the stage 2 begins somewhere in here. It takes a few weeks for stage 2 to begin having effect because there's already these cases that are in the train that are producing new cases, but then the epidemic begins to subside during stage 2, and it continues going down for a time, and we have to identify our parameter mu for this phase, and then it continues to decrease for quite a long time, but then somewhere in this range, it begins to increase again. We enter stage 3. We have a succession of time intervals when the transmission is changing across each time interval. And sometimes it's increasing more rapidly than other times. But the data here shows us what happens day by day for this period of time in Spain. And the data is very surprising in a way because it's so zigzaggy in this end stage here. It's bouncing around like a basketball. And so we have to try to work with this data because that's all we have. We only have that data. Now, I didn't go from October 5th to our present time, October 15th, because Worldometer will revise this data for the past several weeks, typically. So I ended at October 5th, but for our later publications for this work, we will extend up to a later time, and we will do the same analysis for many, many countries. But here I will just illustrate it for Spain. Okay, so how's my time going here? I lost track. I talk until when? Someone tell me.
I think it's until 12:30, correct?
12, no, I think it's 11:30, right? 11:30.
Yeah.
All right, go ahead. Yeah, go ahead. Yes, we have different time zones. Yes, yeah, please. Yeah.
So I have plenty of time. I'm not in a crunch for time.
I know.
Okay, let's keep going. So that's the daily reported data for Spain. And as I say, it's very confusing here. There's this tremendous jumping around that's going on. And I understand that in part this is due to the fact that Spain has a very extended, a very important weekend starting Friday, going through, or Thursday perhaps, and going through the Saturday and Sunday. And there's major changes socially in Spain during those weekend days. And so that may explain some of this jumping around. It's also true in the US, by the way. In fact, almost anywhere the data will be quite bouncy. So this is the cumulative reported cases. Remember, we call that C, capital C, R of T. And we take our daily data and we just add these points up one by one from the starting value March 1st to October 5th. And we see quite a different story. There's a smoothing. Of course, this must increase. And it begins down here in the exponential growth phase. We'll try to identify a region here when it's increasing exponentially. It goes into stage 2 when the government measures cause it to break, to subside. It lasts in stage 2 for a period of time, but then it begins stage 3 and the epidemic starts to renew and increase again with a second wave, in fact. And so this is the cumulative reported cases from March 1st to March 5th. Simply add up those dots. And then we go to what's called the, let's see, what happened there? Clicked the wrong one. Okay, then we do what Jacques talked about. We take a rolling weekly average. And this is very common because we take this terrible data that's jumping around so much. And on day 7, on March 7th, whenever that is, we add the first 7 dots here and divide by 7 to get the weekly average for that day, day 7. Day 8, we take the data from March 2nd to March 8th, divide by 7, and we get the weekly average for that day. And we keep this doing on to the end, and we get what we call the rolling weekly average. And it smooths out tremendously, and it's most useful in trying to really understand what's going on. So we can see from the rolling weekly average how the daily cases are changing with this smoothing effect. We have the initial outbreak, stage 1. Stage 2, the subsiding of the epidemic. Stage 3, the continuation of the epidemic with new outbreaks, new increases. It's always increasing here because this is the, through this interval, I should say, it's increasing, but sometimes it's increasing more rapidly than other times. So we'll identify a succession of time intervals in the stage 3 in which the epidemic is increasing more rapidly or decreasing sometimes even. And we will try to identify those intervals with our stage 3 formalization. Okay, keep up with the time. So now we have to get our parameters for stage 1 in Spain. So we have to go back here and take our cumulative reported cases in this very early stage and find an interval when those dots are increasing exponentially. So we did that, and there's different ways to do it, but this is the way we decided. We go from March 4th to March 11th. The dots are those cumulative reported cases from March 1st to March 16th or something, 15th. And we identify this range right here of those 8 dots as the exponential growth phase. Before that, it was approximately linear. You had the same number of cases day after day, and the growth rate was linear. After, again, it doesn't appear to be exponential anymore. So this is the interval of time we chose as our exponential growth phase 1. Now we must fit a curve of the form a times e to the bt minus 1 to that graph. So we do that, and we use Mathematica to identify the parameters a and b for that phase 1 based on that data. And so let's see, I should tell you what those values are. For A, we got this value, 2005. For B, we got this value. And then we used those formulas I talked about earlier to get our initial time, T0. And it's minus 33 days. So it was late in January, in fact. So this, in a way, this is a bit artificial, but it works. And that's what we ask for this model. We also evaluate the tau 0 value. Remember this rate that was in our formula for stage 1, in fact, for all the formulas. And it turns out to have this value, again, from the formulas based on B and our assumptions on eta and nu. And we obtain our initial values in this way, and we're ready to go with our model. We have the parameters, we have the initial values, and we, first of all, we find out what R0 is. Remember, R0 is based on somewhere. R0 is based on the values of the parameters that we've identified and this B value that we identified from stage 1. So we get a formula for R0. There is the value of R0 for our model, and it's the basic reproduction number in the stage 1, and it's equal to 3.4. It's this value right here, the intersection of those yellow lines. So that's a high value for R0. That's a terrible value for R0. And as Jacques explained, this is the number of new infections created by one infectious individual on average during this stage of the epidemic. And it's based on the value F equal to 0.4. That's the fraction of cases which are reported symptomatic. And it's based on this tau 0 value, which we identified. We could vary those values if we take F. It's hard to read that, but I think F is 0.1 at this point, and it's 0.8 at that point. And we vary tau 0, it's something here, and it increases here. And we can see how R0 varies with these changes in F and tau 0. So this blue graph is the surface R0 as a function of those two values, F and tau 0. Its value is 3.4 at our baseline models. But it lies above this orange plane, which is the value 1. It's 1 on the vertical axis. And so we see the dependence on F. And so it's increasing as F increases. And it's has increase as tau 0 increases. So we can see the dependence on R0 as we vary the value F and we vary the value T0. And we can take the other parameters too. Okay, so we need the time-dependent transmission rate on stages 2 and 3. We have it on stage 1. On stage 2, remember, we assumed it had this expression involving this tau 0 identified in stage 1, but this value mu that we have to identify by fitting, and we take mu to be 0.09 for our particular application. For stage 3, we have these succession of time-dependent parameters for transmission, and we have an alpha n for each of our successive intervals. Tau 2 to tau 3 has tau 2, then tau 3 to tau 4 has tau 3, and so on. And so we identify the parameters alpha n associated with each subinterval. And I should mention that we can claim that the number of cases daily of asymptomatic infectious individual is changing at this rate, which is proportional in that particular time interval to this expression here. So that will be increasing, but we can use that to see how much it's increasing or how little it's increasing. And so here are the values that we chose for Spain for this third stage, for all the stages. This is stage 1, this is stage 2, and this is the successive stages in stage 3. Okay, so have some time left. This is the comparison of the model simulation of daily reported cases to the daily reported cases data. And so the blue graph here is the cumulative reported cases from the model. You can see a blue graph there. And it goes through these purple dots, which are the data very nicely. So we have a good fit to data for the cumulative reported cases. Here's our time frame, March 1st out to October 5th. Now the green graph is the unreported symptomatic cases. And then these two graphs are the reported daily cases and the unreported daily cases. So we see two waves here, the first wave and the second wave. And so that we get a good fit from the model to the cumulative data. Now we want to understand what's going on in all these various time intervals when we're changing the transmission. So as I mentioned earlier, the change in the asymptomatic infectious number of daily cases is approximately equal to this expression right here, which is a multiplier times I of t. So this is going to be this will always be in positive, because the cumulative reported, I'm sorry, I shouldn't say, this is not always positive. It's positive or negative, depending on this expression in the parentheses. It can be positive or negative. And so from that, we get the cumulative reported cases will depend on the sign of this. I should say the concavity of the cumulative reported cases will depend on the sign of this, because CR double prime of t is equal to nu 1 times this expression times I of t. Okay, so we take all our time intervals, and here I've graphed in green the cumulative reported cases derivative, and in orange the cumulative reported cases second derivative. And we see we have concavity up, some places concavity down. Here's an example where the concavity is down, it's C double prime is negative. Through these intervals it's up, C double prime is positive. We can use these ideas to fit the values alpha sub n. Okay, so where are we? We have the cumulative reported cases in the model compared to the daily cumulative reported cases averaged of the data, and this is our fit, model to data with the rolling average for the model. This is now this idea, we take the cumulative reported cases to date. Remember, we had our model giving a good fit to that data, and we extend to December 1st or 5th, somewhere in December. And when we do that, we get 3 different extensions. We have no change in this extension, which starts on October 5th and continues to December 1st. We're extending the model from October 5th to December 1st. If we make no change in that last interval, then the graph looks like this. It continues what we saw earlier with this value of alpha, the last value of alpha. If we increase social measures, then we get this graph, which is very nice because we reduce the cumulative growth. If we decrease social measures, we get this bad graph because we have an extension of the cumulative number of reported cases over to 1.1 million. From at this point, it was approximately 8.5 million. So we can use our model in this way to project into a future what happens in our example. And we can go ahead as long as we want, but it's very difficult, of course, to predict what will happen in a COVID-19 model, because it's a bit like predicting the weather. There's so much that can vary in all the features of the phenomena that is very difficult to include them. But we can identify features, as I mentioned here, and try to understand their influence, their impact on the future projection of the model. And we can take a time interval, perhaps 2 weeks, 1 month, 2 months. It's very difficult to go much beyond that. Okay, I should mention the works that are involved in this project with our authors here. And I want to mention quickly, in 1 minute, the plans for future work. We want to introduce vaccination into this model because vaccination is the great hope for controlling COVID-19. And it will lend itself very well to models such as ours, where we have a background model for the epidemic. We include vaccination. Of course, there's many complications, many things to worry about, but we will try to incorporate vaccination into our model and apply it to various locations, such as this example in Spain. And we also want to, as Jacques mentioned, we want to introduce age structure. The age brackets of the susceptible infected populations are very important in understanding what's going on in COVID-19. So that's another feature that we want to emphasize for the future. So I thank you all for listening to what I have to say this morning. And as I said, I hope everyone is well and will stay well. I'll be happy to answer any questions that anyone may have. Thank you very much.
Thank you, Glenn, for a very concise presentation of a series of your studies. Now, so we can entertain questions through chat or question and answer function, or you can simply raise your hand.
I have a question to Glenn.
Yes, please, Jack.
Yes, thank you very much for this very nice talk. And have you the feeling that the ratio CR over CU is practically constant? What is the dynamics of this ratio?
Well, we assumed that a fraction of cases went to R and a fraction of cases went to U, and then it remains, that fraction just remains indefinitely. So that's a strong assumption. That's not a good assumption.
Of course.
And so that, it was apparent in the graphs, they matched, but we need to consider that more carefully, because over time there's changes. As I said, there's changes in that fraction. And so we want to, that should be part of our future work as well. But that fraction is very important, we know, and it's very controversial in almost every situation. Sometimes it's claimed to be a very high proportion are unreported, sometimes just the same or even less sometimes. We chose that value 0.4 and 0.6 for Spain based on some information about the seropositivity testing. But there's testing that's underway, sometimes telephone-based testing or online-based testing to see what fraction of people have had symptoms and have been infected, but haven't reported. But it's very, very difficult, very controversial.
And finally, the overmortality due to the unreported, this overmortality is constant for you or not? Finally, the mortality is the same in reported and reported or not?
Well, we actually didn't introduce mortality. We could, of course, we could take the data, which has mortality, and we could try to connect it to the model, but we actually didn't do that. We didn't include mortality in any way in the model, but we could, of course. Right. And the same questions would arise about mortality reported versus mortality unreported. And those are very important questions and very difficult questions to answer, by the way, and very controversial. In the US, sometimes it's claimed that there's a severe underreporting of the mortality because they take the average number of deaths in the United States over the past 5 years, and they compare it to this interval of time that we're looking at COVID-19, and they see that we have a much higher number of deaths. So what causes them? And so there's many controversies about the data. It's a big challenge for anyone trying to model or understand or project COVID-19 epidemics anywhere, because the data it's not nice. You have to live with it, however, because that is the data. That's all we have. That's what we have.
You're right. Thank you very much.
Thank you.
Thank you, Jacob. Jane Heflin, you have a question? You can ask directly, I believe.
Hi, Glenn. I have a question specifically about the exponential growth phase. So the data that you use, there aren't very many days that are there. And I found that for some Canadian regions, the exponential growth phase doesn't actually exist because mitigation was brought in early enough so that we can't even really do a fit there. I'm wondering how important that fit is to the exponential growth phase, or how can you account for no exponential growth phase in the model?
Well, I think we would be unable to use this model if there was no identifiable exponential growth phase in the earliest time of the epidemic. And that's true in some locations such as Canada. And I think the reason is once the epidemic got underway, the government imposed measures almost immediately to cause the epidemic to subside. And so that's a case that we cannot really use this model, I would say. And there are other places where that's true, but most locations, it's not true. Now, there may be provinces in Canada, you call them provinces, right? Provinces where there is an exponential growth phase, and we can put our model in work on such a province. we can apply our model to all kinds of locations, nations, states, cities, groups of states in the US, and so on. So, but we must have an exponential growth phase to get it started. But that's a challenge of any model to get it going, to get it parameterized, to get it initialized. And it's especially difficult for this COVID-19 epidemic. Because for one thing, the data is so scratchy and the variation is so extreme. So that's a good question. That's all I can say.
Okay, thank you.
Sure.
So Galen, I have a question about the definition of the epidemic starting time. You didn't go into detail how it was defined, and I think it's a very interesting concept. I just how that, yeah, how this formula was defined. What motivation? How you define this T0 in this way?
Well, you should ask the guy sitting next to you.
Okay,
because this is actually his main idea. The way of fitting this early data in its exponential growth phase, if you can identify it, to some parameters that you then use to get everything else. And
right.
So it's a process that's a bit complicated. And I didn't go into any details, but it's in one of our papers. I forget which one.
All right.
The first one.
So it's a formal procedure. It's a mechanical and a formal mechanical procedure. I forget which paper it's in right now, but it's one of those. And I think it's credit to Pierre for devising something very innovative and very nice to get going with an epidemic model set of differential equations which describes COVID-19. And then, of course, as I said, we develop R0 from these parameters, which is, again, a very nice calculation based on the next generation method of Odo, Diekman, and others. But we assume the new value and the F value and the eta value, we must assume in some way independently based on our understanding of what's going on in the epidemic. So that's separate. But these other parameters in starting time and initial value, particularly this transmission value tau 0 is obtained from this way of this exponential fit to the exponential growth phase in the early stage of the epidemic.
Thank you, Glenn. Pierre, so I don't think you're going to have opportunity to speak in this seminar series, but maybe you can answer this question.
Okay, that's first of all, this is explained in the second paper here among the list in biology. This method has been proposed there, and the idea and used successfully in several other papers later on to several other models, including delay equation, as you know. And the idea is to say that the infectious component is growing like an exponential, right? And so then when you integrate that, you get this shape for the number of cumulative reported cases. And in practically what you do is you first fit, Glenn, could you show Glenn the formula? So, okay, for the CR in function of A and B and C, I don't know which parameter are which one. The CR formula you are fitting with the exponential, that's maybe A exponential BT minus C or something like that. I forgot to, this one, yeah. So what you do is for it, you try several values for C, right? And you take the best, the value for C that is giving you the best fit to the data. You use, then actually you add C to the data, in fact, and you use an exponential fit an exponential fit function to design A and B. And you look at the resulting differences between CR plus C and A times exponential B of t. I mean, because there is no, in fact, there is no method, statistical method to get the best fit. So we needed to design something here. So then we take the C that is giving the smallest difference in between CR plus C and the exponential function. And so this way you can get a pretty good method that gives you everything you need. Well, everything. So, I mean, that gives you some good result later on, in fact, to apply this into the model. But yeah, so I think that's what we are doing now, and this is giving a really good result in many cases, including delay,
And I would say that this value for tau zero is the key parameter. That's the transmission rate in the first stage. And it's based on the fit, the value of B. And it's based on these assumed values, eta and nu in the initial susceptible population. But this is critical in any epidemic model. Understanding the transmission is the critical key feature of the model. And we obtain this parameter from this fit, this way of fitting the data. So there's not a unique way to do that, of course. There's multiple ways and multiple choices for the interval and so on. But for a given application, we can do this. We can find a and a B and a tau zero and so on. That works, and it works. And that's what's important. Otherwise, when you think about it, it's always difficult how to design the initial populations of infected and the transmission rates and so on, the various parameters in an epidemic model. It's always a challenge. So this is the way we do it here.
Yes, thank you. I just thought maybe there might still be some epidemiological interpretation of this initial time. I think it is a very important, really major invention to really.
May I say something more about that, by the way? Because in our last paper in Journal of Theoretical Biology, just appeared today actually, we consider something like 6 or 7 countries, in fact, and in order to compare this exponential phase, the last one here, and there we discuss this exponential phase that is not always really visible from the data, in fact. But still, we can use it, and we can use our method, and it gives some really good result to fit the data also. So we'll stop here about the comment.
Okay, so other questions, comments?
I think there was a question from Enrico Bibona, but maybe it's already answered. So I'll try to find you. Okay, now you can talk. No.
Okay, can you hear me?
Yes, I can hear you.
Okay, thank you. The question is the following. I'm trying also to fit a model similar to your one, and I have serious problems with identifiability. So the parameters nu and eta that you at some point presented, are they estimated from the curves or are they fixed in some other way?
They're guesswork. We consult the literature to try to understand what the claims are about those periods of time. 1 week and 1 week we chose for simplicity. And in some sense, it's an average value. And there's actually difficulties in distinguishing the two values. When do you become symptomatic? you're asymptomatic for 1 week, then symptomatic for 1 week, but is there a perfect division between the two? Not really. You could be delusional about your symptoms, or you could ignore your symptoms. So it's difficult to understand completely the distinction between asymptomatic period and symptomatic period. But we chose 1 week because that's a common assumption, I think. But again, it could vary in locations, in time frame, and there's claims of quite different values, in fact. But we chose that as a simplifying assumption for this particular application.
And these parameters will fix for the whole time period.
That's right. Again, that could be improved because they may change, of course. There's a lot of variability in the population, for sure. And as Jacques mentioned, there's age structure, which is very, very important. And we don't have that. But we want to include that in future work because it's related to vaccination. It's related to mortality. It's related to infectiousness. It plays a very important role, but it's a difficulty for the model because if you have age brackets, how many brackets do you have? 2, young and old, or do you have 50 2-year age groups? Or so the more brackets you have, the more parameters you have to worry about. But nonetheless, it's very important. One way to handle that, by the way, is to use continuous age structure, which we like. And we can, in a way, that simplifies the parameterization issue. But age structure is very important. It was very important 100 years ago in what we call the Spanish influenza epidemic that was so terrible for the whole world and for the US. And age structure was important then because it was the younger people who suffered the mortality. And by the way, there was an asymptomatic infectious period in that epidemic, which lasted a day or two. It was very short, but it was very significant in transmission. So the age structure is a very, very important issue, and it needs to be included.
Thank you very much.
Thank you. There is another additional complication, I think, from my colleague Jacques Bellet. Jacques, you want to ask a question directly, or you want me to do it for you?
I can ask it directly.
Yeah, go ahead.
So, Glenn?
Yes?
A very nice talk.
Thank you.
So one of the issues that's becoming very prevalent in the media is super spreaders. This notion that people have very heterogeneous transmission capabilities. So is there a simple way to enhance your model to have super spreaders, like a more infectious class, or is a complete setup necessary?
Well, we have not, I guess we have not considered super spreaders yet to any serious extent, but it is very important because there's some claims that most of the transmissions come from super spreaders. I should say that.
Yeah, the Pareto 80-20.
Yeah. We have in another project with Pierre and all kinds of people, Marianne Horn and others, we've worked on epidemics in hospitals of antibiotic resistance. And what's known in hospitals that super spreaders are very important for that spread of an epidemic in a hospital. And so we've included super spreaders in those models. And we could use similar techniques for this COVID transmission. We could have a super spreader class. But it creates many complications, of course. But it's probably very important because it's probably true. Most of the cases are transmitted by super spreaders for various reasons, social reasons, genetic reasons, different reasons. But it's an important feature that we should consider, Jacques. I think that's a very good question.
Thank you.
other questions and discussions? If not, then I would like to again, on behalf of all the panelists and the organizers and the audience, I want to thank all the two speakers today. And Pierre, do you have any announcement, or you want me to close?
Yeah.
And
yes, please, go ahead. I mean, I think we are still working on the next session within 2 weeks. But we already got some speaker for within 1 month actually. So this webinar will take place every 2 weeks. But we will have 2 talks every 2 weeks. So because we want this transatlantic confrontation or discussions most probably. And so probably the next session now, soon I will put the information on the web page for November 12th, and we are still working on the next one, which is not totally decided yet.
great. So. Thank you very much again. So for organizing this, and again, thank two speakers, and we're looking forward to see you in the next session.
Okay. Thank you.
Right, so now it's time to close the seminar, so we'll disconnect. Thank you again, the speakers and all the participants for attending. Of course,
something else I forgot to say. We will put the movie, the talks on YouTube, and so we'll be available there. Okay.
Thank you.
Thank you.
All right.
Okay.
Thank you.
Thank you.
Bye, everyone. Goodbye.
Bye.